Everyone comes into class knowing properties of water. They may not be the most unique properties of water. This video is going to talk about some of those unique properties that you are probably most often unaware of. We know that it's clear. We know that it's made of H2O. Some of you might know, again, it's freezing point, boiling point, things like that. But we're going to go beyond. So if you were asked to explain unique characteristics, please don't rely on the things that you knew when you were growing up, going through elementary school, middle school. We're going to learn the high school unique properties. The first one is polarity, and polarity is the result of unequal sharing of electrons between two atoms, which causes one atom to form a positive charge while the other atom forms a negative. So here's your water molecule. This bond right here between the hydrogen and the oxygen is what's known as a polar covalent bond. That's what causes this entire molecule to be polar. It has polarity. There's a negative pole and a positive side pole. Notice the side that has the oxygen has the negative pole. That's due to the fact that in the unequal sharing, the electron that is being shared between the one that started at a hydrogen here, there is one that started as an unpaired electron around oxygen. So there's technically two electrons going back and forth. But what happens is, because oxygen is so large, what will happen, this hydrogen's electron will actually be taken more often over here. So there's an imbalance in the negative aspect. There's more electrons than protons around oxygen at any given moment. So you have this negative side. Hydrogen, because it's lacking that electron, now has an imbalance in the proton's favor, so therefore it's positive. And so water is polar. And because of this fact, really the rest of the unique properties are all due to this. If water wasn't polar, then many of the other characteristics also would not exist. The next one, which goes hand in hand with it, is called cohesion. Cohesion is the attraction between two like molecules. And in order to be attracted to one another as the same molecule, they have to have polarity. Non-polar molecules don't interact with each other because it's the poles that interact with one another. The positive of one side will interact with the negative of the other. As this diagram below shows, three different water molecules. This is the covalent bond between an oxygen and hydrogen. So the positive side of one water molecule, specifically the hydrogen, will be attracted to the negative side of an adjacent water molecule. That's cohesion. This dotted line represents a very important bond. It's called a hydrogen bond. Hydrogen bonds are technically when a hydrogen is already covalently bonded to another atom, but they bond unequally so that this positive charge forms. This positive charge will now be attracted to a negative, as I just explained. So this dotted line is more of an attraction between a positive charge and a negative charge. There is no exchange of electrons between these two atoms. So technically a hydrogen bond is more of an attraction than an actual bond. But please label this as a hydrogen bond, as I have another one labeled up over here. The more water molecules you have, the more hydrogen bond connections you actually can make. These bonds are relatively weak. They are much weaker than that of the hydrogen bond, or the covalent bond that forms between the oxygen and hydrogen. So you can easily pull these apart, and there are environmental factors that pull them apart very easily, such as heat and other sources. Adhesion is a very similar process or similar property as cohesion, but adhesion is the attraction between two different polar molecules. So that would be water and any other polar substance. The most obvious thing in a classroom that you would recognize where cohesion and adhesion are working together is when you're dealing with a graduated cylinder. When you place water into a graduated cylinder, we know that a meniscus forms. That's the idea that on the sides of a graduated cylinder, when you place the water in, it does not go evenly right across. So I'm doing this with there we go. The water is attracted to the sides of this glass. That would assume that then the glass is polar, because the polarity or opposite charges of the glass and water attract. And what will happen is, if one climbs up, the next water molecule is pulled as well, because they're linked together. So the graduated cylinder and the meniscus is actually due to two characteristics: the adhesive property of water and the cohesive property of water. It is adhesive to the glass, but as one goes up, the other goes up. Eventually, the force of gravity will force it not to be able to climb that much. You can't go all the way up to the sides, but there is an obvious meniscus here, so that means that it can go against gravity. Another case is with a plant. Water has to travel up the roots, through the stems, and get to the leaves. In order to do that, water has to go against gravity, and it does that because it is attracted to what is called xylem and phloem, two terms you don't really need to technically know. Just think of it as the stems, the veins that go through the plant. And what will happen is, because of cohesive and adhesive properties, water can travel up the length of the plant. If water was not polar, it would not have this cohesive property, and water would not travel against gravity for any reason. So a meniscus would not exist. Instead, what would happen is, if you would see, basically it would go right across very evenly because it wouldn't be attracted to anything. So that doesn't happen. The fourth property of water is something called heat capacity. And specifically, water has what is very high heat capacity. Many things have heat capacity, or what's known as specific heat. They're somewhat interchangeable. Water has a very high specific heat or very high heat capacity. So just saying that water has heat capacity is actually not its unique property. It's that it has a high heat capacity. It is defined as the amount of energy required to change the temperature of a substance. So based on this, we can say that it takes a lot of energy to change the temperature of water. Hopefully this is evident in the summer when you go to the ocean. In the beginning of the summer, when the sun has just started to become very powerful, it takes a long time before the water actually heats up to a bearable temperature that you can actually swim in. Let's analyze this graph on the right to show how water has a high heat capacity. Energy being on the x-axis, if we are going to assume that 0 would be the starting point, not the best graph here. What this says is from 0 joules to 50 joules, the temperature is going to increase. So this is a temperature of Celsius. So from something negative, maybe this is negative 100 up to 0, which is the point where you're going to transition the states of matter. From 0 to 50, what you get here is an increase in temperature. Temperature is a direct result of speed of the molecule. Something that is higher temperature has more rapid movement of the molecules. So the first 50 joules of energy, according to this graph, have actually gone towards the speeding up of the molecules. So water is still solid, but the water molecules are moving faster. From the point you got to 50 joules up to about 150, notice that nothing is happening. The dependent variable of temperature is not changing. That doesn't mean this energy is going to waste. Instead, what's happening is the transition state between solid and liquid. So what will happen here, the difference between a solid and liquid is the closeness of the molecules that exist. Solids are more tightly packed, which means they have more hydrogen bonds that are connecting between them. A liquid is more fluid, hence the name, because they have less connections between the molecules. There's more space between them. How do you get more space? You have to break the bonds. So this energy that's going into the transition of solid to liquid is not being wasted. Instead, this is going to break hydrogen bonds. So there's about 100 joules according to this, graph that we're looking at here that is required to break all of the bonds that would be needed to transition to liquid. Once those bonds are broken, it's going to be about 100 joules again from about 150 up to 250 that is going to be used to speed the molecules up again. So we have another incline in the graph. So we are speeding up the molecules, not breaking the bonds between them, we're speeding them up. And then at 100 degrees Celsius, or roughly 250, somewhere in between there, all the way out here, this is another transitional period. That means that we are not speeding up the molecules at all. All this energy is going towards is breaking hydrogen bonds. So the energy down here is not being multitasked. Instead, it's either going to be used to speed molecules up or break bonds. It is your responsibility to make sure that you can follow what portion of the graph is it being used for at that particular moment. The fifth type of unique property is surface tension. Water has a high surface tension as well, so you might want to once again add high in front of surface tension, do a little caret there and add it. The tendency for the surface of a liquid to resist external forces is what makes water have a high surface tension. So this is a water molecule, here's another water molecule. All of these arrows in between them are showing actually cohesion. These connections are saying that this water molecule is attracted to this water molecule. So this technical unique property is relying on other properties that water exists. Cohesion, for example. But also it's relying on polarity technically as well. So what would happen is, if forces are acting on the surface of water, water holds this bond. It takes a lot to break their connections in order to break through the surface. Can it be broken? Yes, of course it can. But indications show, such as insects. Insects can walk on, many of them can walk on water. That shows that the tension that forms at the surface is stronger of a hold before the actual force the insect puts on the surface of the water, so it doesn't fall through. we would exert much more force than an insect would. That is why we would fall through. There are other aspects that you would actually recognize. You'll do that in a coming lab. The sixth unique property is that water is known as the universal solvent. A solvent we'll talk about in a few seconds. Mixtures is a terminology that you might be familiar with. It's when two or more compounds will physically interact with one another, but don't chemically alter and or bond with one another. A solution is an example of a mixture. It's a homogeneous or homogeneous mixture. Examples of this might be sugar and water, where you can mix them, you can dissolve. But they are so uniform that you would not actually see the differences in what's within the actual combination. So the sugar blends so well with the water that they become one, and therefore it's still just a physical interaction. It is not a chemical. You still have water, you still have sugar, but they don't interact in a chemical way. The next one, or the next kind of extension of this, solute and solvent. I just said that water is the universal solvent. Solvent is any substance that does dissolving. So water dissolves most everything. Not technically everything, but many things in this world are dissolvable by water. That makes it the universal solvent. The rule for universal solvent, or the rule for dissolving, is actually like dissolves like. So polar molecules can dissolve polar molecules. Nonpolar molecules can dissolve other nonpolar molecules. So that's the technical rule. So that would mean if water is the universal solvent, that means that most things in this world are also polar. In order for a solute, the solute is the thing that is being dissolved. So in the case of the example of sugar and water, sugar is the solute, water is the solvent. All right. There are many cases of solutions. You can think of a carbonated drink as a solution. You can see that there's carbon dioxide dissolved in there. Only when you open it, you can see the bubbles form. That's actually a solution. So the solvent is the thing that's doing the dissolving. Solute is the thing that is being dissolved. Here's an example when water gets mixed with salt. NaCl is an ionically bonded compound. So what will happen here is the water, which is polar, is going to pull apart and attract the sodium and chlorine to separate. It's not a chemical reaction in the sense that what will happen is if you evaporate all of the water away, you still have salt. In a chemical reaction, they alter themselves in a way that they don't go backwards and form a different and go back to the original. So that's what forms that this is not an actual chemical reaction that takes place. The other form is suspension. A suspension is a heterogeneous mixture. It's one that you can see the individual components mixed there. So many times chicken noodle soup is the most obvious example that a lot of teachers talk about. And you can talk about anything from a bean salad, anything where you can individually see the components. That's what's happening. An aqueous solution is just an indication that water is being used as a solvent. Water being the universal solvent doesn't mean that everything has to use water, but if you see that a solution is said that it's an aqueous solution, it's telling you that the water is the solvent. Okay. I hope this explains how unique properties of water have actually made water very special. And we're going to talk about examples in class that say what would happen if water didn't have many of these aspects. But I wanted to get through the content, and this is that video. Thank you very much.